Up to this point in my 386DX build, I have elected to not go with a pair of flash ROMs, but instead go with a quad ROM setup. If you're reading from ROM directly, running code from ROM directly, the 4 ROM setup will be faster than the 2 ROM setup. But the downside, of course, is now I have in my design 4 ZIF sockets, 4 flash memory chips to support this. And I was recently working on a 386SX laptop, and it had just a single ROM. Now the SX would normally only use a pair in the first place instead of quad like the DX would use. But it just made me kind of want to see if I could trim down my 386DX so that I only had a single ROM chip. And that single ROM chip maybe could get copied into RAM during boot up or during initialization, and then run from RAM and have the full 32-bit access to that information. So I get the full 32-bit access. The ROM is basically placed in RAM, and I never have to use the ROM after initialization of the PC. So that sounded great in my mind. Then the question is, how in the world would I actually do that in my build? And I did some searching on the internet, and I probably wasn't searching for the right things, but I wasn't coming up with a lot of solutions. One of the solutions I did find was a chipset like this, the 82C495. It seems that it has the ability to maybe let me feed it a single ROM chip with 8 bits for data, and then pull that into RAM and basically shadow that ROM into RAM, or shadowing. I call it shadow ROM, but here they're calling it shadow RAM. Anyways, using RAM to shadow ROM, whether it's from video or from the BIOS or from something else. This chip is much larger, much more complex, much more capable than I need or where I'm even at capability-wise to really leverage. And it didn't seem like these were inexpensive chips as far as where I could find them today. So I decided to take a little bit different approach and try to implement this in a, I'll call it my own custom quasi-hardware setup to do this. This was the build I've been using, this schematic here with 4 ROMs and 4 RAMs. And that in my last video I showed that I could boot up, I could run code from the ROMs, I could write to and read from RAM and run a basic program, and that was executing fine. So what I want to do though is pull out those 4 ROMs, and I'm going to replace it with this. So I have a single ROM, and all of the logic that I'm going to need to take the ROM and copy it into RAM during system initialization, I want to handle that essentially from a hardware perspective. I don't want to have to write assembly code and figure out how to get at least enough assembly running to then copy the ROM into RAM properly. So I want to do it from a hardware perspective, maybe even before the 386DX processor realizes that it's running, before the reset even, before it comes out of active reset, have everything copied from ROM into RAM. So that's my goal. Now the PSoC I'm using, and essentially inside of it, I'm just doing a design where I'm pulling out the components like counters or latches, transceivers, whatever it might be. And in this case, I'm going to design that out in the PSoC and have the PSoC do the controlling of things that I need to control in this case. And I'll talk more about that in an upcoming slide. But taking out 4 ROM chips, 4 ZIF sockets, replacing it with a single ZIF socket, a single ROM, a PSoC to really do the heavy lifting here. And then I'm also going to need these transceivers that you see down at the bottom. And in my case, when I turn on the system, I need to copy byte by byte from the ROM, but then I need to place them into RAM either for byte 0, byte 1, byte 2, or byte 3. I have 4 different RAM chips, so somehow I need logic that can take a simple ROM with 8 bits of data, read it byte by byte, and get it into the appropriate RAM chip, so that at the end of all of this, I can say jump to a location in RAM and start running my code. and expect all the right bytes to be in the right place. If I look at my address space that I'm maybe set up with right now, this is what I'm using. So the address space of the 386DX, of course, goes much higher than what I'm showing here, but I have 2 megabytes of physical memory in my system. So backing up, these 4 RAM chips to the lower left, they're each half a meg. So I have 4 of those. So I have 2 meg of addressable memory if I can figure out how to map it, basically the right glue logic and what I want to do with it. And I can't use it all. I'm not going to use it all. What I'm most concerned with, of course, is this first 640K, so that'll be RAM. And then I'm going to slice out of the address space 64K that gets me to my video card. So my video card supports quite a bit more memory than 64K, multiple megabytes, but I get to that memory through this 64K window at this address of A0000. So that 64K is to get to my video card. The next 64K lets me get to a memory expansion or RAM expansion card that I built. Again, I can get to it in chunks of 64K, and I can have multiple megabytes in that if I want. So that's going to be at the B0000 address. And then from C0000 through the end of the D, so DFFFF, I'm just going to use that for whatever other I/O I come up with. I have a sound card that's going to need a little bit of an I/O space within that. And maybe other things will come up as I add or expand this system. And then I have this E0000, which is normally where the ROM would be, but this is where I'm going to actually shadow it in. So it's going to be RAM from E0000 up to the end of the 1 meg, which is FFFFF. But that's going to be just a copy of the data from my ROM, my single ROM chip, spread across the 4 RAM chips in this 128K at the top of my first megabyte of RAM. And then above that, I've got another megabyte of addressing that gets me to RAM. So I can access the actual RAM for the first 640K plus the shadow portion that I'm copying my ROM into, plus the 1 megabyte above that. And so here, just trying to show I've got my flash ROM, and that's sitting off to the side. And when I turn on the system, what I want to be able to do is copy the contents of that to RAM, to this specific address, so that when my system runs, that it essentially thinks this is the BIOS area and runs it accordingly. A challenge I ran into, though, is that when the system turns on, the address isn't going to look for FFFF, that area. It's going to look for something higher than that, which is a little bit of a challenge that I had to work through, just making sure I had this set up right. So what I decided to do, and I'm sure there's many ways to do this, I copied ROM into RAM, all of it into this E0000, except for the very last 16 bytes. And the last 16 bytes I actually copy into the top of the 2 meg area. So way up top on this visual here. And the reason I'm going to do that is when I turn on the system, the 386DX is looking at this address of FFFFFF0 for the reset vector of where it's going to start reading code and try to run something. Well, the memory chips I'm using have an address line 18, which is really connected to address 20. And so address 20 is coming from the processor, and when it's looking for FFFFFF0, it's bringing address 20 high, which would bring a high into this A18 pin, which then makes this RAM read at the top of the 2 meg space, not the top of the 1 meg, where I expect I want to start my code, my reset vector at FFFF0. Instead, I got this extra set of Fs there, and that causes some issue. So that's why I decided that I'm just going to copy all of the ROM into the normal BIOS area, except for the last 16 bytes, which I'm going to pop up an extra meg higher. And then when I turn on my system and it looks for FFFFFF0, this A20 is high, therefore this pin that's marked A18 here is high, and it's going to get to the top of that space, and I'm going to have my appropriate jump code sitting there ready for it to run. So that's how I'm approaching this. So the other thing I could have done is just simply tied this pin number 1 on the 4 RAMs to ground and not use the top 1 meg of the total 2 meg. But I thought I'd rather have that extra meg of memory usable. And so this is how I'm working around that. So with all that said, then it gets me to this mess, and I'll just point out a few things here. Maybe just as a reminder, off to the left, this whole card you can pretty much ignore. The only thing it's serving a purpose right now is just giving me a clock that I can pause and turn up and turn down through hardware for debugging purposes. Off to the right is this debug card that I've been using, and a lot of the wiring that you see, these little signal cables are really just getting me appropriate signals to my debugger so that I can log that and use that for troubleshooting. You can see the main 2 ROM slots are empty. I've taken out the card that had the 4 ROMs. I have my 4 RAM chips down here. This right up here is this little set of 3 transceivers. And again, if I back up to this previous slide, that is these down here. And that again is going to allow me so that as I read a byte from ROM, I'm going to have to write it to one of the 4 RAM chips, and I'm going to use logic that's going to dictate which one is actually going to get written to, and I'll talk about that logic coming up. But when I read it from this ROM, it's always on this lowest byte of data. But if I want to write it to the 2nd, 3rd, or 4th RAM chip, not the first one, I need to make sure those data signals get over to the appropriate byte or bits for that specific RAM chip. So I put these transceivers in so I can just duplicate basically the low byte of data to the other 3 bytes. And I'm going to control that through a signal of, am I actively shadowing? Am I in the middle of shadowing the ROM to RAM? And if so, then copy this data. Otherwise, these will shut off and not cause any issues. So stepping forward again, as I look at this, that's what this little card is just simply 3 of those transceivers. Here's the PSoC that I'm using, and here is my single ZIF socket, single ROM or flash memory chip that I'm using that has my entirety of my code that I'm going to run. So the idea is I turn on the system, and this set of components up here should essentially read what's in the ROM and populate the right locations of these 4 static RAMs with what it needs so that I can boot, initialize, jump to my code, and run that code entirely from RAM. Once that initialization is done, this doesn't get used any further, and really this doesn't either, nor does this. So this up here is really just a pre-code running, an at reset type of usage. Now, at the end of the day, the bill of materials cost is probably the same. If I take out 3 ZIF sockets and 3 flash chips, that's probably about the same cost as what this addition of a PSoC and these four ICs over here are going to be. So really isn't a cost difference. It really isn't much of a difference in space that I'm going to need on the board. So instead of these pair, I'll have 1, and then I'll put the PSoC beside it, and I'll have 3 little transceivers sitting around it, so that all should fit in the same type of space. But I turn this on and I need to do some copying. To do that, I have to make sure I can figure out how from that PSoC to generate the appropriate signals to write to those RAM chips. So there's 4 of them. I'm going to have to put an address out on the address bus. I'm going to have to take their basically their chip select or their chip enabled, bring it low to say I'm going to enable the chips, and then I'm going to enable one of them to write to it. So there's a write enable. I have 4 of them, and I'll have to pick one and say I'm going to write to it, make sure I get the right byte of data to it, and then stop writing, deselect it for enable, go to the next one, and cycle through 4 bytes in a row from the ROM to fill up 1 byte in each of the RAMs. Now to do this logic, to basically generate an address, get it out there, manage the CE and the WE, the chip enable, the write enable, I ended up putting into that PSoC logic that looks like this. And this looks really busy, but it really isn't that bad. well, let me just point out some of the key highlights. All of these things that you see over here that say YFB, X, OE, these essentially are, for all practical purposes, allowing me to do tri-stating. So if I have a signal, let's just say I come over here and I have a signal that I pull in here. This is bit 9 coming from basically what I'm going to say is the address. So I'm going to generate an address over here, and I'm going to come into bit 9 starting at 0. So this is the 10th bit of the address. I want to output that, but I can basically say only output it if I'm in the middle of this initialization where I want to fill in the RAM with a copy of the ROM, the shadowing. And if that is the case, that I am in the middle of that, then I'll output this. If I'm not currently shadowing, if I finish the shadow initialization, then this allows me to just simply disable. You can pretty much just think of it as this is a transceiver that I have disabled. So all of this noise, all of these symbols that you see is basically just how I'm doing a transceiver inside of the PSoC. And I have a lot of signals that I have to put out there. So I have to generate an address. And if I step back again, I need to generate an address and then the CE, WE type of signals. And so that's what I'm doing. I come over here, and when the system is reset, so an active low will come in from my reset circuit, I'm then going to basically start a counter, and that counter is generating my addresses. So I'm going to start at address 0, and I'm going to work my way up to 1FFFF. So 1FFFF is the stopping point. That's the last address I want to copy from ROM to RAM. And I'm going to look for that address. And if I get to that address, that means I've worked all the way through it. And then I essentially disable this routine. What this circuit is doing gets disabled at that point. And I say I'm no longer in the process of initializing the shadow. I have an LED indicator on the little PSoC. When it's lit up, that tells me it's actively copying ROM to RAM. And once it's done, it'll shut off. I also have the address latches around my processor are controlled with this signal here. And so basically, if I'm in the middle of shadowing, setting up this copy, I will disable the latches so the processor doesn't see anything on the other side of the hardware latches that I already have on the board. So essentially, I'm isolating. I'm saying disconnect the processor, let this PSoC take over all of the address lines during this initialization. So that's kind of what I work my way through here. There's a little bit of code, or not code, but this compare here. What I'm doing is if I get to 1FFF0, then I enable the A20 line. And by enabling the A20, that basically means it's going to write this to the top of the 2 meg space instead of the 1 meg space. That was that 16 bytes of the actual reset vector code that's going to do a jump and jump to actually where my code is going to start running. So I've got a counter. It's going to generate every address that I need to read from the ROM. It's going to look for the end of it, and it's also going to look for the last 16 bytes and move the last 16 bytes to the upper 2 meg if that is the case. Something else I did in here, I also put in a little 3-bit counter. So it's basically going to count from 0 to 7. And I'm using that to generate essentially timing. So back to that RAM, I had to have certain timing. And here in the upper right, I'm supposed to have my address be valid first, and then maybe have my CE be valid, and then my WE. So there's kind of an order of things that I need to work through here. So this is how I implemented that. I'm sure, again, there's many ways to do this, but what this is allowing me to do is say, okay, take this clock that I'm running this off of, which is a 12 megahertz clock, and divide it into 8. And for the first, 2 clock ticks of that, just have everything be high. So I haven't set the address, I haven't set the chip enable or the write enable. But once I get to this 3rd clock, take the chip enable, the CE, and bring it low, activate it. So activate my RAM chips. And then on the next clock, go ahead and start writing out to one of the RAM chips, and then stop the writing, stop the CE, and then cycle my address to the next address. So this is just a way that I'm dividing up this 12 megahertz clock into 8 pieces, and I'm controlling and trying to get timing that'll kind of work like something like what you see here. And if I back up, then that's generating a clock that is going to turn on my write signals to the chips, and I'll come down to this in a second. It's also generating when my address should move up an address, basically go from address 0 to 1 to 2 to 3, and also when I should just generally have my RAM chip enabled or active. Now if I am going to write out to my RAM, I then have to choose which of the RAMs I enable for writing, and so then I'm just using A0 and A1 and only doing this when my write is low. So the write has to be low, and then I'll use the A0 and A1 to determine which of these 4 RAMs I'm going to actually go ahead and write to. So that's essentially the gist of this, is build me some type of clocking that will let me get these signals built out to do something like this. Count from the first address all the way up to the top of the ROM addressing, and essentially put that stuff out onto the bus. I do also send out a signal that lets the rest of my circuits, my other PSoCs, for example, know whether or not there's currently this shadowing process going on. And so if I step forward to one of those as an example, this is my decode on my main system board. When should I turn on RAM or ROM or whatever it might be? Again, I put in these tri-states so that I can disconnect these. And if I am currently actively in the middle of that shadow process, I disconnect all of this so these won't conflict with what that other PSoC is doing. But once that shadowing is done, then these of course become normal and do their normal job of, am I in a RAM output, RAM write, is my chip select or my chip enable, is that set? And up here you're going to see that I'm always going to send out a 1. So if I'm not shadowing, I'm going to disable the ROM, and I will never use that ROM again. So the ROM is only read during the initialization, and then it's essentially turned off. And I've started to put in some logic of just decode logic here, at least for the RAM. I've got the first 640K, when am I going to turn that on? When am I going to turn on, access, or when am I accessing the shadow ROM? When am I accessing this reset location? And I have more work to do here, but this was enough to at least get the basic functionality up and working. And later, like I have a to-do here, I might put in some logic that if it is within the shadow ROM range, that I could prevent writes to it. And that's easily done. Just I have to add a little bit more logic here for that. And then the final thing I had to do is go into my code, which this is the simple test code that I'm still running. And I just had to come down here towards the bottom and put in that instead of jumping to, previously I was jumping to a C000, now I'm jumping to an E, because I cut my ROM size in half from 256K down to 128 total, because I don't need 256 and I'd rather have that addressing available for something else. But I had to update this to basically jump to the proper location. So then that gets me to something like this over here. And what you're seeing here is my system is off in the lower right, and I'm just pulling up this little debug tool that I'm using. Again, this is that debug card off to the right, and that STM32 that's fetching all these signals. And I turn on my system, and in an instant, and I'm going to pause this video here and actually bring it back, but pretty much in an instant, it copies over the ROM to RAM in less than a second. And as I replay this, what you're going to notice is this LED here on the PSoC lights up when it's actively doing the shadowing process. It's taking the ROM, copying it to RAM. And you're going to see that when I turn on the system, it lights up just momentarily, 1 second, less than a second, and then it's off. So it did the shadowing. And then my processor at that point, the way I have the PSoC set up is it lets the processor out of reset. So it holds the processor in reset while it does that copying. Again, I have everything tri-stated so that there should be no conflicts on any of these signals between the processor and that PSoC. But then it lets the processor out of reset. The processor now is going through its normal initialization, and that takes quite a few cycles. So this takes a bit as it goes through this. But then you're going to see that once it gets through this, it's going to start reading at FFFFFF0, and there that goes. And if it works right, it should then jump to E0000, which it does. And you can see now it's going from E0 to 4 to 8, and it's working its way through this. And I'm going to pause this a couple times here as I go, but for example, if I take a look at some of the signals here, what I'm looking for is, am I doing, well, first of all, ROM read. You shouldn't ever see that active again because I'm not using any ROM anymore. But then you'll see if I'm doing a RAM write or a RAM read. And when I do a write or a read, I can go to the left and look at, well, what address and what's the data. And in my little test code, I'm basically writing to a location of this 05AC for the address. And I'm just incrementing a counter. I'm calling a procedure, it increments a counter, or basically this variable, this memory location is just going to increment what's stored there. And so like here I can see it's writing a 1 to it. And if I continue this, I can then watch for the next write. And if I get to the next write, right here, I can see it's writing to FFFE. That's my stack. So that would be where my stack is. So it's writing something to the stack. And that's probably when it's going to make a jump to a routine. So it's writing down where it needs to come back to. And it needs to come back to address 11. Let's see, within my space here. And if I keep going, there it does a write of a 2 to the 05AC. And I'll let it keep going. Next write will probably be again to the stack because it would have returned. Now it's going to call it again. And so then I'm looking for a write, and there's a write. If I pause it, again, it's writing to FFFE. That's the stack. Should have incremented, so now I'm going to see that it should write out to my variable the next value, which is now a 3. So it took the 2 and moved it up to a 3. And in the meantime, it read that, so I can look for the lines that show it reading it, writing it, etc. But I'll let this run as I continue to talk here now. But that's what essentially this program is doing. And I'm zoomed back, and you'll kind of see part of the waves up above, just so I can kind of see what's happening. And as I look at that, I can look at, when does my RAM CS or the CE go low? When does the read go low? When does the write go low? And then which specific byte on the RAM chip am I writing to, or bytes? And 386 might write to 1, 2, 3, or all 4 of them. And so you might see different patterns there. But at this point, this is working. And if I just continue to let this run, I see that as this is scrolling by, I'm kind of watching for those writes, and I can see now they're incremented. It was at, let's say, a 6, and then it's going to come around to a 7. So everything's working. It's running my code. My system started up. It pretty much instantly, for all practical purposes, copied the ROM to RAM, jumped to the proper spot in RAM, that is essentially my ROM code, and is now executing that program without any issue. Maybe something I'm going to do next is I am currently using a 1 wait state here. I think I can go to a 0 wait state. I don't see why not. So I might experiment with that. Just flip this over to a 0 wait state. I'm starting to get a feel for how all the wait state stuff is working, and within the logic of my PSoCs that are managing the wait state. I'm getting more comfortable with what I change there and how it impacts the behavior of the system. So that's all I had for now. At the end of the day now, I am down to a single ROM chip, which is great. I'm tempted to order up the next revision of this prototype board just to include the single ZIF, single ROM chip, add this other PSoC, and get these three transceivers basically added to my board. And I think I'm going to move all the debug headers off to the far right edge or to a different location, so I don't need any wiring, straddling across my board as I'm doing this debugging, just to make it a little bit cleaner to work with. And I've also realized, which control signals I want to get over to that debugger outside of what's on the ISA bus. So I might try to just clean all that up and make it really easy to connect and disconnect that debugger and make things nice and clean. The other thing I want to do maybe before I order the next revision of the board is just validate my coprocessor connections, at least according to the technical documentation, if I think I've got those right, because I might not have those right in the current build as it sits here. So more to come, but this I thought was a nice step for my build. Really doesn't move the functionality of the system forward yet, but it's going to make just working with it a lot easier, as I'm only going to have to update one ROM chip every time I want to change the code on it.